3D bounding boxes from a YOLO model combined with a depth map. I've created a new repository, basically just a library that you can go in and use that combines YOLO. So we take the 2D bounding boxes, we use a depth map, so we can use pretty much any model that we want from Autolytics, YOLO, object detection model. We just need a 2D bounding box. Then we have a depth model. Right now I'm using Depth Anything 2, but we can also use the Apple one that has metric depth. But any depth model can pretty much be used. We just combine the 2D bounding boxes from our object detection models with our depth map, and then we project that into 3D space. So I'm pretty much just making this open source library here that you guys can contribute to as well. So if you want, you can go in, add new features, functionality, maybe just upgrade it a bit as well. So this is just something that I've just released and published, and we're going to build out here in public as well. So this is pretty cool. I've seen a lot of demos, videos and so on with 2D object detection, but we need to be able to take it to the next level and also get it into 3D space. The good thing here is that we can then train an arbitrary model on our own custom data set. We can take the pre-trained models and then basically have 3D object detection up and running. I played around with a lot of other different types of 3D object detection models. They're either very hard to set up, or secondly, it only works on very specific classes. So that's mainly for research and so on. We want to be able to use our projects and applications out in the real world and build some very nice projects. We need to have our own custom class. We need to be able to just take a model, use the depth information, project it into 3D space, and use that in our projects and applications. So I've just opened up my GitHub profile here. You can go and check it out. Start a repository. I have a bunch of different repositories in here. I called it YOLO-3D. So this is what we're going to build out. This is just the initial push that I have done that we're going to walk through now, and then we're going to build it out over time. So we have a detection model, we have a depth model, we have some bounding box 3D utilizations. I really need some help from you guys. Like, if you want to contribute to it, definitely just go in and fork it, make some modifications, and then create a pull request once you have some cool stuff up and running. We should create some better visualizations. We should create some better 3D accuracy, some different modes that it can be in for the 3D accuracy as well. Maybe even have different options for the depth models, whether you're looking for relative depth information, absolute depth information with metric depth, and also how we can basically just scale it, maybe have some references in our image as well to make it more robust. So this is a very good way to build in public, contribute to different repositories, learn a ton on the go, because most people, they only focus on the 2D bounding boxes. It's so easy with Autolytics and all these frameworks here to just go in and train a model in 5 minutes. That's not really a computer vision engineer. We need to dive deeper, actually solve problems and cases. So I will have my computer vision software, have my AI career program where I'm creating a ton of different tutorials too and so on. Definitely check that out if you're interested in getting into AI career, getting into AI machine learning engineering roles, computer vision engineer roles. I'm helping people out with that, whether they want to land a job, freelance work, and so on. But it's just so nice to actually build out these things here instead of just the traditional demos. I've seen so many different computer vision engineers. They can only do Autolytics run. It's basically 3 blocks of code that we need to run. It's way more about building systems. So having experience with object detection, instant segmentation, post estimation, and so on is pretty much worthless. So this is a good way to build projects on top of it. We can even build projects on top of it. So right now we just have the library that we can use to get the 3D bounding boxes. Then we can build systems on top of that as well. So here's the features: real-time object detection using YOLO-v11. You can go in here as well, start, or you can also fork the repo if you want to do contributions. So real-time object detection using YOLO-v11, we can specify whatever model that we want. Depth estimation using Depth Anything 2. Then we have some features for 3D bounding box visualizations. We should definitely build out more features, functionality, and visualizations. We have a very simple bird's eye view. This is also an area that needs more work. Object tracking capabilities, support for video files and webcam input, and then also adjustable model sizes for performance accuracy trade-off, but also just making this depth map here fast as possible, because this is the main downside, or like the main limit right now on the speed. The YOLO models, they're crazy fast, but it's going to take a lot of processing to calculate the depth maps. We could even have a faster version that just goes in and does 3D bounding boxes based on default size, average size of different objects that we already know from our data, and then do some estimates or references based on the size of our bounding box that we're getting in the 2D space. Requirements, pretty easy. You can just walk through this README file, clone it, seed into it, pip install the requirements, and then we have this run file that takes care of all of it. So inside the file, I'm going to show you the code editor and run the program and so on in just a second, show some examples and have the live up and running. But we have input, and also going to create tons of videos around it so we can see how it improves over time. You guys are doing contributions, we can do some videos around that as well, cover the specific features and build software systems on top of it. So we have the source. As we know, we can just specify 0 for default web camera or a video path file. Output path, it's also going to write it out to a new video file so we can save the results that we're getting. We can choose the model size that we want, have all the variations from Ultralytics, nano, small, medium, large, and extra large as well. We can also use V12, 10, 9, 8, or whatever. Even also other different types of YOLO models. Then we just need to implement those features to support the output bounding boxes from that. Even RoboFlow inference could be integrated into it as well. We have Depth Anything V2, small, base, and large model that we can choose from. Confidence threshold, intersection over union threshold, and also the classes. If you're using the pre-trained model, we have the Coco classes, 80 different classes of various types of objects, phone, person, truck, car, and all those. If we have our own custom models, we can also just throw that into it. Have tons of videos covering how we can train our own models, run inference and so on. So now it's way more about building systems. I want to push my computer vision system, my AI career program. We get all these AI agents and so on. How can we combine that? I teach the people inside the AI career program and basically just have the mentorship, trying to teach people, okay, what direction is it actually going, how to build out these systems by yourself, put your work out there as well, because if you want opportunities in life, that's pretty much the most important. Enable tracking, we need tracking as well, just for smoothing out our 3D bounding boxes, so it's not just like jumping around in the image frame. We actually want to have it smooth, tracking the object, both the 2D bounding box, we don't want that to jump too much, but also especially the 3D bounding box. So we have Kalman filters, basically just tracking the state, making predictions, and so on for filtering our 3D bounding boxes. I have the bird's eye view as well, so we can see how far the objects are from each other. That's pretty cool, but definitely needs more work. Project structure, how it works, and acknowledgements here. Right now, if you want to use it, you can fork it, or you can just go in here and git clone it. I'm going to open up my cursor editor. We see we have the files over here to the left. This is the main file, run.py. Let me just make it a bit bigger here so you guys can see what's going on. We have everything here, the same README file as we just went through. We have our depth model, detection model, load camera parameters. We can also take camera calibration into account. If you want to be an expert in camera calibration, I pretty much cover it in tons of different videos on my channel, both the theoretical part, how we can do it for a stereo camera, a single camera, how we can pretty much just do it in 5 minutes, and I go over what it can be used for and so on. I also have my camera calibration software, load camera calibration or camera parameters if you want to use that, or we can just use some default estimated ones based on our image size. So let's go inside and run. First of all, we import all the different modules, libraries, and so on that we need. I have checked running if it can be hardware accelerated when we run the inference on both MPS. So that's for Apple hardware for now. Could maybe integrate MLX into it as well for even faster inference. It checks for CUDA if you had an NVIDIA GPU, so it runs significantly faster if you run it on a GPU compared to what I'm going to show now. We're going to run the YOLO models. I'm on a MacBook M4 Max chip, so it's a pretty good CPU. And also GPU, it's going to run on the CPU and also MPS, so it's real time, very fast processing that we get just from a MacBook. But if we have a CUDA GPU, it's going to be significantly faster. Could even go in and optimize the models for TensorRT, use that with Ultralytics just to make them run faster, but the main bottleneck is the depth map. So yeah, we have our detection model, we have our object detector class from there, we have our depth model, depth estimator, and this is the only things that's inside those files for now. We can build it out if you guys have any good features, classes, anything that we can build into the system here to make it better, more accurate, more features that people can use in their projects and applications out of the box, feel free to like throw them down in a comment, throw them on GitHub, forget, like basically just jump on the train and help me out build this system. I'm going to push it a lot on my YouTube, like create different demos, videos, and so on around it as well. We have our 3D bounding box utilities. There's a lot of stuff going on in there, trying to do some different estimates, some visualizations, just handling the 3D bounding box. Definitely need more work in there as well, but also for the visualizations with the bird eye view and how do we get better accuracy on our 3D bounding boxes. Because right now it still estimates based on the depth map, which is a relative depth map, so it depends on what objects are in the scene. So it's basically just relative to all the objects that we can see from the camera. But we also have some depth models. They're a bit slower, but they have metric depth information and can actually like get down to a few centimeter accuracy. All the things that I'm talking about, I have videos covering it, courses and so on going into the theoretical part. So definitely make sure to check out the other videos that I have on YouTube. Here we're just combining everything together. This is the different variables that we saw inside the GitHub repo in the README file that just specifies what we want to use. We have the device, confidence score threshold, intersection or union, the type of model we want to use, the source, and also our output path. Here we can specify a path to camera parameters if you want to use a camera calibrated or a camera which we have calibrated already. Then we need to create an instance of our object detection model, model size, confidence threshold, and all that. It's just going to run the inference where we pass an image through. We get the output results, bounding boxes, confidence scores, class IDs, and all that as we know from Autolytics. I'm going to show you the file in a second, but let's just go through the pipeline so you can see on a higher level how the whole system is connected before we dive into the details. Then we set up a depth estimator, the model size, and also the device that we want to run it on. It's going to fall back to CPU no matter what, so you can just specify whatever you have here, for example MPS. So if you can't run that on MPS, it's going to fall back to CPU. You can also have it just automatically detect the system that you're running, but I'm just forcing the CPU right now because I'm doing it on my MacBook, and we get the most speed up if we have an NVIDIA GPU. There we go. We have our bounding box 3D estimator. We're going to create that. The code is pretty well documented, commented and so on. So if you're not 100% familiar with what's going on, you can read more details in the comments instead of like watching the videos and so on. But it gives a high level overview over how it works and also each of the different functionality and features. We create our bird eye view. So this is going to be like just some bird eye view that we create in the corner. Definitely need more work for that one. We need to have better accuracy, better tracking, could be just better estimates, alternative approaches and so on. So this is just one approach. We can have multiple different approaches depending on the references that we're using, the estimates that we're doing, or the depth map model. Right now we're going to just create our bird eye view. Also need more work for visualizations and just making it more accurate. Set the frames per second. We also set up a video writer so we can see the results or just store a video file. Have the number of frames per second. We have our while loop, which is basically just gonna load in video frames. So just keeps going, loading in frames from our video file or our webcam. We create an original frame, we do a copy of that. We have our detection frame, we have a depth frame, and then we have a result frame where we just combine all of it together. The first step in our pipeline is running object detection. To take our detector class, run our detect method. We throw in a frame and we enable tracking if we want to use tracking on top of it. Then we're going to get our detections and also our detection frame, which we're drawing our visualizations and predictions on top of. We put a text here if we get any errors and so on, and we have our detection frame, so detection error. Now we go down and do our depth estimation. We have our original frame, we estimate the depth with our depth estimator, we get our depth map, we can colorize our depth map so we can just visualize it to better see what's going on and how good our depth map is. Then we create a dummy depth map here, basically just for our color depth map. We don't really need to do that if we're not able to estimate it. if you're able to load in a frame and so on, it's just gonna like throw it through the estimator. You will get some results back, but we have fallbacks for pretty much all of them if we run into any errors. Once we have done the detections, we have our depth map, then we need to do our 3D bounding box estimation. So we take our 2D bounding boxes and we want to project it into 3D space based on our detected or estimated depth. We take our detections, have a for loop running through all the detections that we get in the frames. We get a bounding box, a score, a class ID, and also an object ID for our tracked object. It's basically just going to track the objects over time. So if we lose, like for example, detections on one frame, it's still going to keep that object because we track it even though the object detection model is not able to detect it any longer. We get the classes from our detector. If we have a custom model, that makes pretty good sense. So we can pull the classes that we have in our own dataset. Right now we just check if we have a person, cat, or dog. We can also check for all other different types of different objects, and then we basically just take our depth value, depth method, center medium, then we can get the depth in a region or get the depth at a point. So we have our detection model. It will probably be better to integrate into segmentation. I'll do another video where we just run it through segmentation, compare the results and so on, but that's how easy we can actually swap it out. So instead of looking at the bounding box and then just taking the center point, then we can actually go in and use the mask. So we look at the whole mask and try to fit a 3D bounding box around our mask, because if we have an instant segmentation mask, we can just mask that out and cover it out directly in our depth map. Then we just have each individual pixel, which we have classified as a person, for example. We have a RGB value, we have the position, and we also have the depth value. Then we can project that into 3D space and try to fit a 3D bounding box around it. So we have these different cases. You can play around with them. Maybe sometimes we want to get for the median depth in a whole region. Could also be that we just want the center point. So we definitely need to play around with this part. Could be way better with instant segmentation as well, but it should just work with both cases. Then we create a dictionary with all the things that we need pretty much. So we have our 2D bounding box, depth value, the depth method that we use, the class name, object ID, and also score. Then we can track that through our whole video. Doesn't matter how we move around, or if we lose track, or like if we lose predictions of our objects, we're still going to keep track of it and try to still get the depth values for the 3D bounding boxes. So then we're going to append the 3D bounding boxes into our boxes 3D. We can clean up our trackers. Now we just iterate through our 3D bounding boxes and do the visualizations. So now we just go through our 3D bounding boxes, or pretty much just all the information that we need to do to take our 2D, project it into 3D space. First of all, we're just going to set the colors here depending on the different types of objects that we're detecting. Then we can go down and actually do the 3D bounding box. We have our result frame. So this is just going to be where we draw it on. And then we have our results box 3D, and our box 3D is both our 2D bounding box, depth value, depth method, class name, object ID, and score. So that makes more sense once we jump into this bounding box 3D estimator. If you want to have the bird's eye view, it's just going to do some visualizations here, calculate like the region of interest, distance between the objects and so on, and visualize it. This also needs more work. This is just some fast boiler code that I threw together for this initial push. Then rest is just adding FPS to the output, setting up the depth map, setting up both all the display frames, so the result frame, the depth colored, and also our detection frame. That's pretty much it. This is the whole pipeline that we have. I'm going to create a separate video where we go way more into details with the bounding box 3D utilities. We can set up some default parameters or default dimensions, which is just the average of the objects that we have in our dataset or in the Coco dataset. Right now that is not used, but could be very interested to see, can we use that information to go in and make it more robust, make it better in the 2D space, and maybe even get around our depth maps as well. Then we can estimate our 3D bounding box. We take our 2D box, depth value, class name. We do a lot of calculations. I'm going to go into details for that in another video. So basically just have 600, 700, 800 lines of code. Most of it is just visualizations. So maybe 500 lines of code in total for all the 3D work that we are doing. Inside our detection model, load camera parameters, we also want to have a calibration script. I'm going to create that in here, but I already have that on my YouTube, GitHub repository and all that, so you can just use it out of the box. But it's going to load the camera parameters, create a projection matrix based on our camera matrix. So we have our intrinsic and extrinsic parameters, where we have our 3x3. We can even have distortion, so we can undistort image and all that as well. That's a whole nother story. If you're not familiar with camera calibration, definitely check that out. It's also a pretty cool computer vision topic. We have a rotation matrix and also translation vector. How is it rotated and also how is it translated? We can apply camera parameters to our estimator if we have it, or it's just going to use some default values. So this is what we're going to use based on our camera height. It's going to set that as the default. We have our detection model. It's just an object detector. We check for the different devices, so we can run faster inference. We check for MPS, CUDA, and also CPU. Have the model map with all the different variations that we can choose from that we have available now with Ultralytics. We get our MAD model, we get our model name, and then we can just create an instance of our YOLO model in the exact same way as we're doing with Ultralytics. This is going to take care of everything. It will download the model automatically the first time we run it, and we can specify any model here. Even if you have a custom model, you can just throw in the path to the model here, and it's going to take the rest and do it automatically. We set our confidence, intersection or union, max detections that we want. We have our detect. So once we have our model created, initialized, we can have this detect that we called with our image. So we just throw our image into it. If you want to track it, we're going to detect it and return our annotated image, but also our detections list with all the information that we need. So if you use tracking, it's just going to call model.track, throw in our image and the device. If we are using out tracking, we can just call the predict method from Ultralytics, throw in the image and also our device. We can set verbose equal to true if you want to have like pretty much all the detections that we're getting in our output terminal. If you're using tracking, it's just going to run through all of it, have a folder running through all our bounding boxes, throwing it into new list that we can then throw back, or like just return from our function. It's going to draw the trajectories if you want to have your trajectories for all the different items that we're tracking. So we track it, we get the trajectory just going to be the center of each bounding box, so we can see how we track the objects over time. Combine that with our 3D Calman filter for the smoothing of our 3D bounding boxes. So it's starting to become a bit more technical, complex and so on. If you're not following 100%, make sure just like watch the video again, read through the comments, read through the code. You'll understand a lot from that, but every single topic here is either covered on my YouTube channel. Pretty much all of it that you need is covered on my YouTube channel. If you really want to dive into the technical details, like all the theory behind the filters, the tracking algorithms and all that, I have courses going into the math and the theory as well, if you're interested. All my technical courses is also covered inside the Agree program. You can find all the information on the website. Definitely go and check it out anyway. Like it's I think it's a pretty cool website. I'll probably just link it to it up here. And we return our annotated image and also our detections. The rest here is just for drawing all the bounding boxes, the class ID, confidence score, and so on. We have our depth model. This is our depth estimator. So this is how we can set up depth anything too. I just chose that model because it's pretty fast, it's very good result, and it's also easy to set up. Right now we just use the pipeline from Transformer, so we can pull it directly from Hugging Face. We can choose between these different models, the exact same class structure as our detection model. So if you want to do customizations to it, it should be fairly straightforward to just go through it on your own. Make modifications, do a pull request with new cool features. I would love to like read through the code, like work together with you guys on creating something really cool open source here. Haven't seen like a lot of people basically just trying to get these YOLO detections or the 2D detections into 3D space, because that unlocks a whole nother world of opportunities in computer vision. We have our estimate depth function. We throw in our image, we convert it to a PIL image. We throw our image through our pipeline, we get our depth map as the depth results, and that's pretty much it. This is what we can go in and return. We normalize our depth map to values between 0 and 1 just for consistency as well, and then we can scale it due to estimation. So this is just relative depth values. You could If you have metric depth values, you have your camera parameters and all that, you can multiply it with a value to get it back again to our real absolute scale. So we normalize it, and then we return the normalized depth map. The rest is just applying color maps, get depth at a specific point. So we have an XY coordinate, we have our depth map, we just take our camera, take a single point, and we get that depth value for that. So let's say that we have a full mask for instance segmentation. Each of those will just be an XY value. You just have a coordinate system. The image is just a coordinate system. We have the X-axis, we have the Y-axis, we take a single point, and if we take each single point in our instance segmentation mask, we can get the depth value at each point in our instance segmentation mask. I think this could be a very good approach as well, and we should definitely integrate it into this. Really hope you will help me out with this one. We can also get the depth in a region, so defined by a bounding box. We get all the mean values inside our bounding box. Median, mean, and min might not be the best approach. I think the points, or basically using instance segmentation with the average of the instance segmentation mask depth values, will be a much better approach. This is pretty much covering all of it. We went through the whole pipeline, the GitHub repository, how everything is structured. We have the 3D bounding boxes as well. We draw the boxes, we do some predictions with the depth map to get it into 3D space. We create the bird eye view. Let me just scroll up here as the last thing. So the main function that we're working with is project box 3D to 2D. It can also project it back again. We have a filter, a camera filter running, so it's just trying to have a prediction. It has a state and it has a prediction step, and then it basically just goes in a loop back and forth trying to estimate where it's going. So there's a lot of stuff going on in the Kalman filter as well for our 3D bounding boxes. We could maybe apply some moving averages or something like that to make it even more simple, but we have the Kalman filters, which is also all the other 2D object tracking algorithms that I have inside my course, like byte track, byte sort that it's using Autolytics. They're also all based on the Kalman filter under the hood. So it's really good to understand the Kalman filter if you want to get into tracking, statistics, and just some of the math behind it. Estimate the orientation, backprop point, so we can backprop a 2D point to 3D space. We're going to take the intrinsic parameters of our camera. We take the inverse of that, so linear algebra. We have the point in 2D. We multiply that with the space, and then we just multiply that again, do a matrix multiplication. So this one here is basically just going to take our 2D point, multiply with our depth value, and then it's going to do a matrix multiplication with our inverse of the camera matrix. So yeah, then we can scale the coordinates, have the references and all that. We can play around with it, but this is pretty much the main function that we are working with. The rest is visualizations, estimating the 3D bounding box, as you can see here as well. We have another video like going through every single line of code in this box or in the bounding box 3D utilities, because that's where most of the hardcore stuff is going on. Hope you learned a ton. Definitely go through the video again. Help me out with building this. If you have any cool suggestions, if you spot bugs, features, just let's build out something very cool here that a lot of people can use in the future as well. You'll gain a lot of experience, a lot of exposure, and most important, like get your work out there, get experience, like work with cool people on nice projects. That's pretty much what everything is about. So let's now get to the more fun part, where I'm actually just going to open up a terminal. There we go. And we can just run python run.py. It's gonna open up the web camera in just a second. There we go. Using device CPU, we initialize the different models. Now we get the camera up and running. So we get a bottle, a dining table, a person, we get a chair, potted plant, and a potted plant here in the background. So this is just our 2D bounding boxes, but we are still running object tracking. Let's try to take the bottle. We can see we have the trajectory that we are following as well for our tracked objects. It's not real time because we have the depth estimation model running, and we are also running on CPU. But this is the depth map that you can see. This is pretty awesome, and you can get some really good depth values, relative depth values, if we just used instance segmentation as well, as we discussed when we went through the code. Next one here, it's gonna pretty much be our 3D object detection code. So we have our 3D bounding boxes. We can see the potted plants in the background here. Let's move to the other side. There we go. Looks pretty awesome. It uses the medians to get the center of each 3D bounding box, and we're going to track it as well. We have the bird eye view down at the bottom, which is basically just going to have the relative position toward each other. So we can see 1, 2, 3 meters here. It's probably pretty good with the background, how far the objects are from each other. So we have a lot of empty space over here, which we can see in the bottom. We still track the objects here in 3D space. Looks very cool. We have the 3D bounded boxes. Still a lot of more work to do, but we have some really good boiler code that we can use as a baseline. So thanks a lot for watching this video here, guys. Definitely going to check it out. It's so cool, awesome. I really hope that you want to contribute. At least give it a star. Let's see how we can build this out. Follow me on LinkedIn, any platform, whatever. Check out my website. And then I hope to see you guys in one of the upcoming videos. This is definitely going to be something cool. Until then, happy learning.